Okay, I guess we are live. Um, just share my screen. Uh, can you guys see my screen?
Yes, sir.
Okay, good. All right. So we'll yeah. So welcome to week 5 of the live session for your course Intro to Machine Learning. My name is Rajvi Jain and I'm a PhD student in IISc. Today's agenda is we'll do the week 4 practice questions and the quiz questions. So I understand that there's some sort of a uh, not so much clarity regarding the solutions and the problems there. So we'll take some time and do that today. Okay, and figure out what doubts you have. Okay. Mm, okay. All right. Yeah, and as usual, my whatever I've written here and whatever we are having the video will be recorded and will be shared with you guys. And I do understand last time there was some issue with the recording of the live lecture, so I've made some adjustments this time. Let's see if it occurs once again. All right. Um, all right. So we start with week 4 practice questions. Is that okay? So can you guys see the question? Week 4 questions?
Yes, we can see.
Okay, good. All right. So the first question, which of the following are convex functions? So any idea how you would solve such a question? What are the different ways of solving such a question? If you had to.
Yeah, if I just volunteer, we can first find the individual component function and see what how the component convex functions, if they're convex at all, how they're combined, and whether that composition is at all convex.
Okay. So okay, let's question 1. Yeah. So one idea was to see the composite functions and how they are combined, right? So in case we are able to break that function down into composite functions and see how they're aligned, in case it's a proper we can do some small tests here to see if the resultant function is also a convex function. Okay, what else?
First order conditions for convexity, if we can find those.
First order conditions, yes. So do you know what are the first order conditions?
Yeah, it's I a little bit forget. I'm not particularly absolutely sure. Means you have to test whether the function lies below the tangent line, something along those lines. I'm not completely sure.
Right. So del f of y, if I'm not wrong, this is what exactly it is. So del f of x plus y minus x into, there is something here. Okay, so this one particular method, I'll get the exact expression after a while. Okay, so this should be true for any y and x. Okay, belonging to the space of the function, right? The domain of the f. Okay, what else can we do? So this is for checking for convexity. Yeah, what else can we do? So we also have second order conditions, right? Second order
Yeah, second order
conditions. Yeah, second order conditions are basically the Hessian
Hessian, sir.
should be PSD. Right? So if it is PSD, this implies that the function is convex. This is one other thing. What else actually? There's one more, in a way we can look at the epigraph of the function and stuff like that. I've never personally used this approach, but this sort of will lie basically using geometric sort of a proof to understand if the function is convex or not. Okay. Okay, so we'll do the second approach, the third approach, the second order conditions approach. Okay, so we'll look at, so the first thing actually, the first question is a bit simpler in some sense. So we have been given f of x equal to sigma sigma I equal to 1 to n xi power p power 1 by p, right? And given that p is greater than or equal to 0, right? Yeah, and x is in Rn. Okay, so what does this thing actually remind you of in some sense?
I just thought it's AMGM inequality if we can apply here. I just thinking.
Yeah, okay, yeah, correct. So we can apply that sort of inequality also, correct. So, but then there is some other issue actually. So, okay, so that's one approach, obviously. And this is somewhat similar to your norm, pth norm of x.
Yeah, P norm, yeah.
Pth norm of x, right? So LP norm of x. Now, so if you know, so norms basically have this triangle inequality, right? So triangle inequality in norms basically tells this: x plus y, p is less than or equal to xp and yp, right? So in that sense, so basically the approach of this one, so I can write this 1 minus theta y if it is less than or equal to theta times f of x plus 1 minus theta times f of y. If this holds true for all xy in the domain of f, right, and for all theta belonging to 0 1, then we can say the function f is convex, right? So if you just put these values here, right, you'll be able to see that this thing holds true. But there's one small caveat here. Anybody want to try? So if you've tried the the problem, your answer, the solution is not, so one is the function given is not a convex function. So any ideas why that might be? So ideally the thing is, this triangle inequality is for LP norms, but this is for p greater than or equal to 1. Okay. So the way to prove it is a bit straightforward, but the idea is that when you prove for p equal to 1, what you do is you take the limit under p tends to 1. For p equal to infinity, you take under the limit p tends to infinity. Okay, and you prove for any value between p greater than 1 less than infinity, you can prove this thing. This is all fine. Okay, but for p less than 1, this thing starts failing. Okay, so hence in that scenario, your first function is not a convex function. Okay.
Why it fails for p less than 1? Is it evident from the function itself?
From the function, it may not be evident actually, if I'm not wrong, because I think there are some other things here to be done. What else we can do is we can look at Hessians and try to do that. But I tried that approach, but it was getting a very very complicated. But yeah, so this I found to be a bit intuitive in some sense, right? Because we know how norms work, and we know that LP norms are actually norms only for p greater than or equal to 1. So hence the the answer is not true for other p values.
And here p belongs to reals, right?
P belongs to reals. Yep. So p greater than or equal to is 0 is generally belongs to reals, correct? So yeah, R plus basically.
Yeah, but p less than 1, why doesn't roll? It looks a bit non-convincing. I'll have to find that out.
Okay. So yeah. So I also do one thing. I'll get the formal proof properly in the next class. Yeah. And we can probably discuss then. Yeah. Okay. The second question is basically f of x equals to log of sigma I equal to 1 to n e power xi. Here the given xi given to r power n, it's actually x belongs to r power n, where xi are the components of x. All right. So the function is like this: f of x equals to log of sigma I equal to 1 to n e power xi. and yeah, so x belongs to r power n. So if you want to take the derivative of this function with respect to a given component, so does this make sense? Just let me know. Is this right?
Yeah, but one I shouldn't be there, right? Which you are taking the derivative respect to the I. That variable shouldn't be there in the numerator, right?
Right, correct. So yeah, so just be careful that when you take this derivative, this with respect to some components, and this I is basically just a summation index for this. Okay, so ideally, so this is not right. And what I do personally while solving such kind of problems, I just take xk to be very safe. So here the thing is, this will be as it is because it's a log of anything 1 by x, that is fine. And then this is going to be I equal to 1 to n dou by dou xk of e power xi, right? Now wherever k matches I, only there that derivative will exist, otherwise it will be 0, right? Wherever it is not, because with respect to k, that particular e power xi becomes a constant. So what happens is you just get this I equal to 1 to n e power xi, and then you'll get 1k exactly will match. So that will be e power xk, and d by dx of e power x is e power x. So you get e power xk. Okay, is this clear?
Yes, yes.
Okay, so this is the first derivative. The second derivative, when you take with two approaches, right? So dou square f by dou xk squared is one thing, and dou square f by, let's say, some dou xj xk. Okay, so where here,
Raj,
yeah,
Raj, I had a small thing. Means, can we prove it by direct comparison? Because the exponential functions are convex, and then we are taking an affine combination, taking the log. So that thing should be a convex. Can we prove it like that?
I have to think about that actually. So affine combination, yes, that is fine. Logarithm.
Log is a convex function, right?
Hmm.
So the affine function, you are suppose g is the composed function, which is affine, which is convex, and then you are taking a log of which is there is also a convex. So probably the final answer should be convex if we go like this.
Right.
I'm just thinking out loud. I'm not sure.
Right. Huh. So yeah, it makes sense. But the thing is, I guess, yeah. So the idea is that can we prove it rigorously or not? I think that's my approach always has been, right. If you can prove it
Yes.
without a shadow of doubt, right? That should be, I
Yes.
mean,
Yes.
yeah.
How convincing the proof is.
Yep. Yep. Yeah. Okay. So with that, again, I will say, this becomes your summation I equal to 1 to n or whatever e power xi, and you'll expand this, and you'll get some nasty looking equations, e power xk minus xk into, again same thing, you got dou by dou xk of this equation, so you get e power xk again, right? So yeah, so we'll get as xk 1 to n e power xi e power xk squared by e power xi squared, right? So you can actually write this, we'll put this on as gk or something so that it becomes easier. Gk minus gk squared, and then similar thing if you do here, you will get this we have e power xk by summation I equal to 1 to n e power xi, and as we can see, this first term will become 0 because dou by dou xj of e power xk, e power xi, and e power xk will be here minus, and then you'll get e power xj. So this is basically minus gi gk, right? So you have found what the individual derivatives are, double derivatives are. So your Hessian matrix will be something like this, right? It will be g1 minus g1 squared, and then minus g1 g2, and so on up till minus g1 gn, and so on. You will get here minus gn g1, and so on, then gn minus gn squared, right? So you need to prove that this is basically a PSD. So is PSD. So this proving is a bit involved in some sense, because then you need to this becomes a bit irritating in some sense. So this actually will come down to yeah. So I can write this actually as G1, G2, and so on, a diagonal matrix of this form, minus G1 squared, sorry, G1 squared, G1, G2, up till G1, Gn, again G1, Gn, and Gn squared, right? So this basically is nothing but, so what we found del f, right? This is basically just del f times del f, okay? So so we'll name it as S in this case. So this is basically a matrix of this format. S times S transpose, and then this is diagonal of S. Okay, we need to prove that any x like this for all x, right? This happens. Okay, so in trying to prove this, what you will need is something called as Cauchy-Schwarz inequality. Any idea what Cauchy-Schwarz inequality is?
Yeah, yes, I forgot. The product is less than equal to something. The
Right.
product of the individual numbers.
Right. So
Is
let's say
equal to less
we
than-
have let's say we have two vectors u and v. The inner product, that is
Okay.
u transpose v. Yeah, u transpose v is less than or equal to
Modulus u. Yeah.
yeah. So your u transpose u times v transpose v.
Yeah.
This, I think, this is squared. Yeah,
Square.
correct. Yeah. Okay. So this is the one. So this is actually a very good proof. So I'll say, try it out once. You will be very glad if you get like how to move from this location to your using this. We need to prove that this is a PSD matrix, right? Hessian function. Okay. So I'll leave it at that for now, and in case you have any doubts, just put on the discussion forum. We'll do the whole proof the next time. Make sense? Okay. Okay. The third question, similarly, we have summation of sine xi I equal to 1 to n sine of xi. So same thing you can do basically. You'll get dou f by dou xk. In some sense, this will become cos xk, and dou square of dou xk squared will become minus sine xk, and dou square f by dou xj dou xk becomes 0, right? Because this is just a function of k. I mean, depends on only xk, so xj will become 0. So in this scenario, we kind of lucked out, because now what happens is your Hessian turns out to be a diagonal matrix, right? Because all your non-diagonal elements are 0, diagonal matrix. Now, and in diagonal matrix, we know that the elements of the diagonal are your eigenvalues, right? So, and the thing is, your so what is in the diagonal? In the, you have minus sine xk, right? So your eigenvalues in this case of this Hessian matrix can be negative. If it is negative, I mean, because it can be negative, Hessian is not PSD, right? So HF is not PSD, so therefore this is not one of the answers. Okay, and I think I'm not sure. I think there's some issue with the coding, the answer sheet, but yeah. So third one is not a convex function. Okay. Similarly, you will get for your fourth one, which is f of x is xi log xi. Okay. You will get HCN to be a diagonal matrix. Okay, in such that your each of your um, diagonal values, diagonal entries are positive, right? So therefore it will be a PSD. Okay, and actually in some sense I think PD, because I don't think it will be 0, I guess. But yeah, you have to check this. But yeah, but yeah, it'll be PSD, right? You'll get this as clean like a diagonal matrix. Okay, any questions in this?
I just wanted to ask whether do we have to always go down this route of taking a second derivative and a Hessian and this thing, because it looks a bit time consuming, right, for a multiple choice question.
Yes, true. But yeah, so at least I am again. It's my personal this one that doing it in this way gives you clarity as to how does something work or not. But again, there are multiple ways to prove, and hence we discussed the first thing, right? That there are multiple ways to prove this. You can go about in any
Yeah.
of these routes, which is fine. That's not a problem.
Yeah. Okay.
Yeah, sure. That's not a problem. Yeah, fifth thing is that same the actual definitions, that is minus theta value. Yeah. But yeah, so make sure you keep all of these things handy, because then sometimes it may be difficult to prove it in one way, as we saw in this in this approach. Doing it like this may be a bit time consuming, and as you suggested, right, we can look at it as a logarithm of affine transformations of convex functions. So that may be
Yes. Yes.
a simpler proof to go ahead with. Yeah. All right. Good. So yeah, question number 2. Any doubts here? So the right answer is, here the thing is that we're saying that we have two approaches to classification. One is we have discriminant functions, and one we have hyperplanes sort of an approach. So which is most suitable for multi-class problems? The first two are not right, because both of them allow for a probabilistic interpretation, right, of the predictions that we have. Because I can always look at probability. The probability of belonging to one class as a distance from the hyperplane, or as a value of the the discriminant function, obviously normalized. So I can always do that in both of these methods. The second and third, third and fourth. The fourth one basically tells you that we can use a base expansion for transformation of the input, which is not true, because that is not something which is specific to these methods of hyperplane, right? Because these are basically your kernel methods, where you can move any input to some other space, and then basically apply some sort of a linear transformation, linear classifier in that space. So third one is the right answer, and it says that because having appropriate set of functions will allow us to efficiently disambiguate class predictions, because then we can say, okay, how much farther or how much cleaner is this particular sample belonging to this particular class or not, right? In that way you can try to understand this. Okay. Any doubts here? Okay. Good. So yes, the third problem. Have you tried anyone this problem? How to solve this problem of optimization? So how would you go about doing this, right? So this is a constrained optimization problem, right? So one basic thing is that you need obviously some sort of Lagrangian functions here, right? So how would you go about doing this?
Yeah. Yeah, you absorb the inequality constant into the Lagrangian, into the optimization objective, put a lambda there, the Lagrange multiplier, and you take the double derivatives with all the Lagrangian with respect to the x and the lambdas both. You end up with two equations.
Right.
Equate them to 0.
Correct. So third one is basically when you have something like this, minimize f of x subject to some constraints. Right. So what you do is you form a Lagrangian. This is called as a Lagrangian. Right, where you say f of x plus lambda times the constraints. Right, constraints as some algebraic expressions. Right. Now the idea here is that what you will do is you will say, okay, I will minimize this function first with respect to x first. Okay, so I will do dou L by dou x, right? And I'll also look at dou square L by dou x square because I need to make sure that it is a minima. This tells me if it is a minima or not. This equal to 0 gives me some value of x in terms of lambda, right? Let's say that is something like x hat, right? So x hat is, for example, let's say some h of lambda, right? Now what I do next is I substitute that h of lambda comma lambda in the Lagrangian. This becomes a function of lambda, g of lambda, right? And then I maximize this, right? So maximize g of lambda subject to some constraints. This will be a simpler thing to do as compared to solving these constraints altogether. Here you will get things like lambda greater than 0 and all of that. So what you can do is you can just treat it as unconstrained and then look at the solutions, and then you can choose which one satisfies the constraints. So in this case, when you do this approach, what will happen is you will get strong duality. Okay, strong duality is basically, let's say you do this, you got a value of lambda, right? Lambda star, and you know how to get x from lambda because that is x star is equal to h of lambda star, right? Now what you do is you put this lambda star in g of lambda, find out g of lambda star, find out f of x star. If these two are equal, then we say it is strong duality.
Raj,
yeah,
in the tutorials I just went through, there was some pre-recorded tutorials in the NPTEL course. There it is said strong duality holds when there is a saddle point, means the infimum and the supremum can be interchanged. That condition I'm having a little bit difficulty in understanding, getting my head around.
Oh, yeah, no, I'll have to think about that actually. So okay, so what is that exactly? Infimum and supremum?
The primal problem and the dual problem are there, right? And when I do not clearly exactly remember, I just went through his slides. There was some person in IIT Bombay who was giving the tutorial.
Okay.
So he was saying that problem, that is a strong duality holds when this thing can be interchanged. When the optimal point is the saddle point, that means the limbs supremum of the infimum is equal to the infimum of the supremum, something of that sort.
Okay.
But I am not exactly sure. I can share you the slides, means or raise it out in a discussion forum. But I also having very difficulty in understanding that.
So the idea is this basically, right? So the thing is, see, you will what you ideally want to do is something like this, right? You will maximize this, the minimum with respect to x. Okay. Now the point is that I can exchange these min and max operations. I can say maximize with respect to lambda and minimize of the minimum infimum of this particular thing. Okay, and hence this whole idea comes in, right? When you say, okay, I will minimize with respect to x, so you get you solve for your dou L by dou x equal to 0, and you prove it is minima, and then put that value in g of lambda, and after that you maximize g of lambda. Okay, so here this interchange holds only in some cases, and I think they're saying it holds only for strong duality. Is that what you're?
Yes, correctly. Yeah.
Okay. Good. So I also have to check and come back on this. What I understood was that you at least the method what I remember is that you interchange and go ahead, and then you say, okay, do you find strong duality or not, by checking the difference between these the optimal
yes, then there are status conditions and KKT conditions will come in.
Right, correct. So yeah, to your KKT is where you start coming up with these conditions, lambda greater than 0 and stuff like that, and where it holds, where the constraint is active, inactive, and stuff like that. All that comes here, right? Yeah, but I get the point of infimum and supremum changing, because that's what happens here, right? You change your
Yeah.
min max to a max min sort of a problem, and then try to solve it. Okay, so
Yeah,
so I'll do
what
one.
will happen is
So I'll
that,
do one thing.
yeah,
I'll just go through
you
the
form a supremum on a lower bound, and you try to approach that from above, something of that sort.
right. Yeah. So I'll do one thing. I'll go through what has been spoken exactly, so that I don't want to contradict them. So I'll
Yeah.
just make sure what is read, what has been told already, and then we'll see whether it is right or whatever. Yeah.
Yeah, I think it's right, but the explanation is a bit hard to get around.
Got it.
That's the thing.
Sure.
Yeah, it's correct only. Yeah.
Makes sense. Okay. So yeah. So we'll do that in the next session. Yeah. Sure. Good. So okay.
Thank
So
you.
yeah. So here, yeah, you'll get 1 and 3 as the answers, and the thing is, see, so once you do this dual objective, you will get g of lambda to be like this in this format. But why this is not the option is because you also need the conditions on lambda. So okay, so when you solve this problem, you will get like lambda has to be greater than or greater than -1. Okay, so you are actually solving this maximization problem with this constraint, and then and that's how your fourth point becomes valid. Okay,
So
cool.
this is the feasibility, right?
Sorry?
Feasibility condition, right? This is the feasibility condition, right?
Correct, feasibility
The
condition.
primal feasibility.
Correct, because so what will happen is you'll get here x hat to be something like 3 by 1 plus lambda or something, and then your dou L
Okay.
dou square L by dou x square will become like I think some function of 1 by lambda square or something.
Lambda square.
I'm not sure. Yeah. So what will happen here is for this to become a minima, you will need lambda to be greater than -1. Otherwise, you will lose out the minima. Hence the condition. Yeah. Okay. Good. So that's the other thing. All right. So question 4. Question 4 is true about Perceptron classifier. It can obviously learn a OR function because again it's a very straightforward thing here. 0 0 0 1 1 0 and 1 1. So what will happen is these sorry, this belongs to one class, these belong to different class, right? So obviously this it will be able to learn a classifier, Perceptron classifier will be able to learn OR function. So for a linearly separable problem, there exists some initialization of the weights which might lead to non-convergent cases, which is not true. So we have the Perceptron convergence theorem, which tells you that if data is linearly separable, okay, separable, then the Perceptron algorithm will be able to find a hyperplane. Perceptron algorithm will find the hyperplane. Will find a hyperplane which separates it. Okay. So the hyperplane that it finds depends actually on the order of the points that has been present in the training process, right? Because the way this functions is that it keeps on updating its weight vectors based on whatever data has been obtained. So it says, okay, did I have a mistake or not a mistake? If there's a mistake, it will basically adjust its weights accordingly, right? So depending on the order of the presentation of these train data points, what will happen is it will basically end up in a different position compared to a different order. So that's the reasoning why this particular thing is true. All right. Then okay, next question is 5th. Which of the following is true regarding an SVM? So for two-dimensional data points, separating hyperplane learned by a linear SVM will be a straight line. Right. Yeah. Okay. Then you have, in theory, Gaussian kernel SVM can model any complex hyperplane. This was told in class, right? Because we have this RBF kernels, right? Which are basically infinite dimensional mapping of your data points, right? So therefore what will happen is, ideally speaking, you can separate anything in infinite dimensions. So ideally it should be able to learn any sort of a hyperplane here. Okay, for every kernel function used in SVM, one can obtain a equivalent closed form basis expansion, which is not true, as we know in RBF kernel, because it's infinite dimensional, we cannot find a closed form solution for the basis expansion. And then overfitting in SVM is a function of number of support vectors, which is also true, as you can, again, it's very intuitive in some sense, because let's say you have a lot of overlap sort of thing, right? You will need some sort of a, you will need more number of support vectors to learn such complex functions, right? And these complexities is where you have overfitting coming in place. All right. Okay, so that's the fifth question. Sixth question, the question not exactly clear. Again, I've told that to the course TAs, they will fix it in some days. So the idea is that we have a two-class problem. Which of the following is true? So first thing is a classifier can be learned using the perceptron training algorithm, which is true because the data is linearly separable. This perceptron algorithm will be able to find a hyperplane. Linear SVM will not work well, which is not right. It is sufficient for this data, right? Because I can find this hyperplane using your linear SVM methods. A non-zero C value is essential for this data, which is not true, right? Because so non-zero C value is required mainly for your soft SVM sort of a thing, where you have some sort of a complex overlap in your data points. Here they are clearly separable, so we don't need it, right? Again, seventh one also straightforward. So they're saying which one will have the most impact among these four mark points on the boundary of the SVM. As we know, SVM's boundary depends on the support vectors, and support vectors are basically any point which are nearest to this plane, right? I mean, in this case, a curve. So here basically number one will be the solution. 8, 9, 10 is again programming based. We will do the programming in the quiz section, and yeah, from there we'll move ahead. All right. So the first question, any ideas on the first question? You guys would have submitted by now, right? So any doubts here in the week 4 quiz questions?
Raj,
Sorry.
Raj.
Yeah.
Yeah, the problem is that it's a bit ambiguous. I have told Kaushiki also that there is a modified iris data set, means it specifically asks for some quote unquote modified. I do not know what it means by modified. I couldn't attempt those questions at all. That's the problem.
So modified. So we had a announcement actually made for this particular, exactly this reason, that how to get this modified data set.
Yeah.
Yeah. So yeah, there was an announcement on this as to from where you can get the data set actually.
I missed that. My bad.
Yeah. If I'm not wrong, it should be here.
I missed that.
Yeah. Okay. So ideally, yeah. They're not here, is it? Okay, but yeah, so there was the email sent to the students where where we discussed that, how to get this modified iris data set, and from there you could have used that. Yeah. Okay.
But I didn't get an email as to the best of my knowledge. I don't know. Yeah, probably. I did not think I get.
Okay, so I'll confirm with the course TAs, and in case if it is not sent out, then it is not right to take them into consideration. If that's the case, we'll get it clarified.
Most probably.
Yeah. Okay. Good. So we'll get that done. Yeah. So again, so in this case, your first question, using a basis expansion of this format, 1nx cube, right? So the data points are like this. -1, -1, 0 and 2, if I'm not wrong, and y is 1, -1, 1, right? So here, if you plot it on a line, basically you can see that let's say this 0, 1 and 2, -1. So 0 has -1 as your class label. Let's say I'll mark it with x, and this is a circle. right? So we cannot find any linear separability. So basically, in a straight line, it would just mean like finding a point which I can say above this class and above below this class and so on, right? So here we cannot do it. So let's say if I use a basic expansion of phi of x equal to 1 and x cube, okay? So here, so what will happen, right? So your points are now in two dimensions. Let's say I'll call this dimension 1, which is always 1 by the way, right? And dimension 2, which is x cube, right? So what will happen is you will have one point which is 1 and 0, right, which is this point. 1 and minus 1, this point gets mapped to here, 1 and minus 1, and 1 and 8, let's say this is some 8, right, which gets mapped here. So again, it is not linearly separable, right? I cannot find any line here which can separate the two classes. Incidentally, if I used x squared as my expansion in some expansion or transformation, do you think we would be able to find a linear class here, linear function?
Is it one x square or only x square in the basis transformation?
No, just x square also. No, I need not always move to a higher dimension. I can just, so phi of x now becomes just a feature engineering feature vector.
Yes, now I think it should be separable, right?
Right, because what will happen is your 0 is 0 square is 0.
Yes.
1 square is 1, which is this, and 2 square. So sorry, minus 1 square is 1, which comes here, and 2 square is 4. Let's say, right? And therefore now I can find like a point something here which says that we have two classes, right? That's one way of doing it. Okay. Then okay. Yeah. Consider a linear SVM trained on n points, and we have k is equal to 2 support vectors, and n is more than 100. And they're saying that if I remove one labeled training point and retrain the SVM classifier, what is the maximum number of possible support vectors in the resulting solution? Now this is actually a straightforward question, because what we're saying here is that what is the max number of support vectors, right? So in any SVM, the max number of support vectors will always be the whole data set, right? So if you have n, then it's n. Now in this, what they're saying is you had n, you removed 1, and therefore maximum possible is n minus 1, right? One very simple case to visualize this could be like this. For example, if you have something like this, right, and you have a line like this, okay? So if I were to remove this point, okay, if I remove this particular point, what will happen is that your separator now depends on all these points and this point, right? So basically n minus 1 point. This is again just one visualization of how this could happen, how n minus 1 is possible, is one such possibility. Yeah. Okay. Next question. Which of the following are valid kernel functions? Again, this is very straightforward from the lectures of sirs, that all of these are he actually just had he mentioned everything in one go. So 1 plus, let's say, x transpose z power d, or e power, just use this x of minus gamma x minus z squared, and also tan h of I'll use a and b just to keep it simpler, right? These are your kernels between x and z, for example. X and z are 2 points here. Okay, so this actually, yeah.
Sir, actually in this question, the third one, right, the exponential kernel, the 2 was written little larger, right? So I thought that it is not square and it is number 2.
Okay.
Okay, that's why I didn't actually, please check the question, right, sir? It has not written as square.
No, but even then it will be a kernel.
Okay.
Yeah. It'll be,
Okay,
because
thank you.
yeah. So okay. So actually, so I'll just give as a reference to you guys in just in case if you want it. So how can you construct kernels from kernels? Basically, this is in Bishop book in Kernel Matrix chapter. So the idea is that given any kernel, can you construct new kernels from using these methods. Okay, so I'll encourage you to look at this particular method and try to prove these things, why these things work, right? And then you will be able to appreciate why that mistake that in some sense that they had, minus gamma, let's say it's exp of minus 2 gamma times x minus z is also a kernel. Yeah. Okay. Yeah. So ideally, yeah, it'll be, because then it's like a function of the distance between 2 points, and yeah, so that'll just I mean, e power minus of the distance, and that'll turn out to be a kernel. Okay. So
Raj,
and ideally,
Raj,
just a second. I'll just
yeah,
finish this. So ideally speaking, tan h is exactly not a kernel. You have some conditions under which tan h can be a tan h of this form can be a kernel. I think the conditions are a and b have to be positive. But again, so but the thing is, again, like this was mentioned in the class, so I'm just saying that you can just go ahead with choosing this as your as one of the options. Yeah, go ahead. You had something.
Yeah, I just wanted to ask which Bishop book you were saying, the pattern recognition or the older one, the pattern recognition one, right?
This is the pattern recognition one. Yeah.
Okay.
Yeah. Yeah, should just write down that name also. Pattern recognition. Yeah. Good. So that's the another thing. Okay. Question 4. Okay, so question 4 and all of these are, I think, based on the no, okay, this one is straightforward. Okay, so you have the data set here. They've asked you to use support vector classifier to find out which is support vector or not. So here the answer is wrong, obviously. The question is which of these is not a support vector. It turns out that one is a support vector. And I think you just now had this Kaushiki session, so where I think you would have discussed about how to use sklearn's support vector machine. Again, the method is straightforward. You can just use import your SVC, look at x and z and x and y, and you'll get your support vectors in this format. So 4, 7, 1, 8 are support vectors. So 1 is a support vector, and the answer is wrong. I've told them, then they'll just correct it after a while. Yeah, so that's problem number 4. Problem number 5. Any ideas? Anyone want to tell how to solve 5? Why would the margin be larger in K2 transformation compared to K1?
Yeah, it's such a scaling factor. Right? 3 is a scaling factor, so the differentiation will be more, right?
Correct. Yeah, that's exactly it. So one way to just discuss about this would be that your points, basically whatever are there. So when you do K1 transformation, let's say your points are d units apart. In K2, what will happen is they'll become just 3d units apart, right? And therefore margin is what? Margin is just the distance between I mean the width of the your hyperplane in some sense, right? So it's telling you how far are your two support vectors from the hyperplane, right? So this will also basically become 3x. So approximately speaking, it will become 3x, and so hence your margin will be larger. Now the thing is, I tried to prove this mathematically. I'm a bit stuck here, but I'll see if I can get you proper mathematical proof as to why this should work, right? And my so the way the intuition works is like this. So so by the way, what is the margin in this SVM sort of a setting? How do you get the margin, by the way, if you want to know the margin? So in terms of your hyperplane, what is the margin actually? 1 by mod w, norm w, sorry. Okay, so let's say your hyperplane is 1 w x plus b equal to 0, right? So 1 by norm w gives you the margin of the hyperplane. Okay, so in some sense we should be able to prove that the margin in the second case is 3 times the margin in the first case, right? So the weight vectors learnt here should follow something like this. right? Now this, yeah, I've tried to prove it, but I'm not able to get it exactly mathematically. So we'll see if I'm able to get in the next by the next section. Okay, but yeah, so the major intuition is this, right? So any distance gets scaled by 3x, right? So hence your margin, which is basically the distance between the two support vectors lying on either side of your hyperplane, will also become 3x, right? So that's the idea. Okay, cool. So then you have the modified iris data set. So I'll just cover this because it was present here. So the link, if you follow, you will get this iris x and iris y CSVs, which are basically your four. So x basically has four features, 150 data points, and y basically has your labels for those 150 data points, right? And then you can use your split them into train and test in this format, which is again, I guess, mentioned in the announcement itself. No, it won't be present here. Yeah, it's mentioned in the email. I'll get the email for you guys in a while. And then you have your different things, right? So Perceptron, we know we can just use this Perceptron algorithm here. With L1 you will get 0.84, ElasticNet 0.82. Okay, and the third, I think the next question was about trying out different values for your support vector classifier for the C, that is your parameter of how much weightage you want to give for your slack terms, and you see that the best score is around 0.96. So 0.96 is your answer. Okay, so I've seen some. There was one example mentioned. There was one code example mentioned in the forum that they mentioned that they were getting different values, and that was because they didn't use header is equal to none sort of a thing. Okay, so because what will happen is pandas by default it chooses the first row as the header, but here there are no headers. The first row itself is the data, so you need to use this header equal to none thing to tell that okay, even the first row is a part of the data set, and that is only when you will get this 150 data points. If you don't use it, you will get 149 data points, which could be one of the ways that you can verify what has been told in the email compared to what you have obtained in your data set. Okay, so that's our time for today actually. Fine, so that's about this, and so see, how do you verify if anything is a kernel or not? There are multiple ways to do it. One is the actual Mercer conditions, which talks about in terms of integrals, and also you have integral f of x, your k, which is your kernel function, f of z dx dz should be greater than or equal to 0 across all data points across the whole real system, and such that the function f has this property: dx is less than infinity. Yeah. Okay, and the fact that k has to be symmetric, so k of xz should be equal to k of zx. Now personally this is not my favorite as such. The other approach to do is you can look at the gram matrix, so the kernel matrix. So kernel matrix is basically let's say the ijth entry of this kernel matrix is just the kernel function applied to two data points xi and xj, and then proving that for any data points that come into this system, your kernel matrix is going to be a PSD matrix. So k has to be a PSD. And then multiple ways to prove PSDs. So you can either look at this x transpose kx greater than or equal to 0, that approach, or you can look at the eigenvalues and prove it is PSD and stuff like that. We talked a bit about this last session, right? We talked a bit detail in about what is PSD, what is PD, and how to construct and look at these matrices. Okay, so I think that's what I have planned for today. Any questions? Any more questions for now?
Raj, since nobody's asking any question, I just had one small doubt.
Sure.
In while writing down the Lagrangian during the class, Professor Ravindran actually put a minus sign in front of the constraint. So I just saw everywhere it is plus, but why use the minus? Means I can share the screenshot if it's needed. Is it arbitrarily swappable?
No. I mean, actually, in some sense it is, but I'll just get you the actual thing. I mean, the way I understood this particular thing was this. I remember solving this. Okay, here we go. Okay, so let's so at least what I know from the way to solve these kind of problems is like this. Yeah, so you have minimize, let's say, some f naught of x, okay, over x obviously, such that you have f I of x less than or equal to 0, okay, I equal to 1 to some m, and hi of x equal to 0, okay, I equal to 1 to p. So then what you do is your Lagrangian x comma lambda and let's say nu in some sense is f naught of x plus lambda I times fi of x over I plus summation over I again, nu I and hi of x. Okay, so and here in this case lambda I has to be greater than or equal to 0. Yep, this is what it is. So basically your constraint has to be in this form, basically less than or equal to 0, right? And then you can use this plus lambda, and where lambda is more than or equal to 0.
Oh.
That's the idea. So so what happens, what ends up happening is you use like this, right? Yi w transpose xi plus b is greater than or equal to 1, right? This, to make it less than or equal to 0, you write 1 minus yi w transpose xi plus b less than or equal to 0, and hence you get this with lambda I mean alpha I, whatever, okay. And in case you want the other way, you can just use the minus sign and
Okay.
it becomes like this yi, yeah, okay.
So he particularly chose this form, right?
Which form he chose? He chose this form.
The second form.
Correct.
The second form.
Yeah, he chose this form,
Second form,
which is just algebraic manipulation. But here the thing is, the lambda has to be more than or equal to 0. Yeah, that's the point. Yeah.
Okay. Yeah, fine. Got it.
Okay. Yeah. Anything else? Any other doubts? Okay, so see, we have been having these sessions every Saturday. I was thinking that the last session before your final exam can be kept for just for doubt solving, because the last session either we can do, I think we have RL as your syllabus at that time. Will be either do reinforcement learning in the last session, or we can do some problem solving sort of a stuff. Okay. So I was thinking that better to have this thing because you'll be ready for your exams and stuff like that. If not, we'll just go with reinforcement learning. Again, it's not a hurry, but just let me know if you have any priorities. Okay. Otherwise, I guess we are done for today. Any other doubts you guys have?
Any clarity is there on the form of the questions? Is it be subjective or all objective types? Means multiple choice questions or a mix?
I'm not sure actually. I'll have to ask the course TAs to get this. Yeah, how they do it this one.
Because we have to prepare accordingly, right?
See, the reason to keep multiple choice for your assignments is that it becomes much simpler to get correction done, right? But the finals would be like a in-person sort of exam, if I'm not wrong. So then in that sense, so there I think it's fine to put that one-time effort and look at not just MCQs but subjective sort of a thing.
Hello.
Yep.
So mostly my senior, one of I think he has done this course, sir. So he said that mostly they are asking only objective only, sir. They are saying multiple choice only. They are keeping. They are saying like.
Oh, is it? Okay, then that's the thing. Sir. Yeah. Okay. Good.
So MCQs only.
MCQ seems like. Yeah. Okay. Anything else? Okay, good. So we'll close the session for today, and I'll get those doubts clarified and come back to you with proper solutions. Okay.
And Raj, one more thing. Will you share the Colab notebook which has the answers to those iris dataset thing, because I haven't done those.
Yes. So this week and also all the previous weeks Colab notebooks are shared in the same folder, which has the PDF versions of the Jamboards also. So it should be fine. You will get that. Yeah.
Thank you.
Okay, okay. See you guys next week. So, bye.
Thank you.